So we're going to start talking about solving equations today. And likely the actual solving process of like doing the same thing on both sides of the equation, that's a bit of review. But we'll go over our basic steps for solving linear equations and then talk about special cases, which is what we'll focus most of our time on today, since the rest is kind of review. So this is 1.1. We are solving linear equations. In one variable. So let's start with what that means. Linear equations in one variable. When we say that an equation is in one variable, it just means that, that there's only one variable in it, which isn't to say that that variable doesn't show up multiple times in the equation, but it just means that the equation only has an x in it as opposed to having both like an x and a y, or it only has a b or an a or whatever the variable happens to be. There aren't two different variables in the equation. There's just one. And then when we talk about linear, likely linear equations are the ones that you first learn to solve. We will be talking about several other types of equations in this class, and it's important to be able to recognize what type of equation you're dealing with in order to figure out what approach to take. And so we're going to talk about how to distinguish between equations as we go, starting with linear equations. Essentially, linear equations have no exponent other than one on the variable, is like the simplest way to say it. However, there's a lot of variations on what it means to have an exponent other than one. There's certain ways we can write that without it actually looking like an exponent. So, for example, a linear equation is like 4x plus 3 equals 2x minus 5. If you distribute and combine like terms, every single linear equation can be written in this form. It'll have no more than one term on each side containing x, and it'll have no more than one term on each side that's constant, so doesn't contain a variable at all. So if it's linear, you can reduce it down to having only two terms on each side at most, right? We don't necessarily need a variable term on both sides. We could just have a -5 on the right. Non-linear, so when we say no exponent other than 1, I did not, there we go, put my parentheses in the right place, there we go. We just mean like no visible exponent, because technically those are both to the first power, right? When we write x, it's x to the first power. We have one factor of x there, but we don't typically write that exponent of 1. So when we say no exponents, we really just mean like no visible exponents. So nonlinear, some examples of that would be like 3x squared minus 6 equals 4x plus 7. So because there's an x squared there, this is not linear. Some of the weird ones, like 1 over x equals 5x plus 2. That looks like I only have exponents of 1, but as we'll talk about later on in the semester, when you have a variable in the denominator, it really represents a negative exponent. So 1 over x is really x to the negative first, as opposed to x to the positive first, and so that is an exponent other than 1. So in general, anytime you have a variable in the denominator of a fraction, it is not a linear equation. The same goes for like square roots. Again, there's a way that you can rewrite square roots as exponents. So even though it doesn't look like there's an exponent on that variable, that square root does represent one. And again, we'll talk more about that as the semester goes on. I just want you to see the sort of funny examples that you would want to recognize as not being linear equations. So really, if anything weird is going on with your variable, it's not linear. So radicals, if it's in the denominator of a fraction, absolute values, things like that, make it nonlinear right off the bat. So we'll talk more and more about how to recognize different types of equations as we start working with different types, but it's always a good idea to start with knowing what linear is before we start talking about all the different other ones. So let's talk steps for solving linear equations. So solving linear equations. So these are likely steps that you already know, but it's a good idea to have it in front of you, because as we get to more complex equations and more abstract equations, so like literal equations that don't have any numbers in them, they're just all variables, it's always nice to go back and have like a concrete set of things, steps that you can follow, and kind of bring it back to basics so that you can know what you're doing in every single step, even when it looks super crazy. So the first thing we're always going to do is clear fractions. And the way we'll do that is we're going to multiply both sides by the least common multiple of the denominators. So the least common multiple of a group of numbers is just the smallest number that all of them divide into evenly. LCM is often used interchangeably with least common denominator. They're sort of the same number. The least common multiple is a property of a set of integers like 3, 5, and 7, whereas the least common denominator is a property of a set of fractions. But it turns out that the least common denominator is the least common multiple of the denominators, so people usually just use them interchangeably because they end up being the same number. So let's do an example as we go here. Let's solve 2/5 x minus 1 equals 3/10 x plus 1/4. Anybody tell me what the least common multiple of the denominators is? Yeah, it's 20. So the smallest number that 5, 10, and 4 all go into is 20. If you used 40, it wouldn't hurt anything in terms of solving the equation. Like, you can use any common multiple of 5, 10, and 4, so any number that 5, 10, and 4 all divide evenly into, you're just going to end up with bigger numbers. So as long as you're multiplying by the same thing on both sides, you're not going to mess up the solutions to the equation by multiplying by a number other than 20 here. But, you know, you could multiply both sides by 10 billion if you really wanted to, but it probably wouldn't be super fun to solve. So the only reason we use the least common multiple is just to keep the numbers as small as possible. So we're going to multiply both sides by 20. So 20 times the entire left side equals 20 times the entire right side. And then I'm going to distribute. So multiplying 20 by both sides really just ends up meaning I'm going to multiply 20 by all 4 terms. So both terms on both sides of the equation. So I have 20 times 2/5 x minus 20 times 1 equals 20 times 3/10 x plus 20 times 1/4. And if you want to start at this step, you're more than welcome to. So you can just start by multiplying each term by the LCM rather than writing that first step if you want to. If that first step helps you keep track of what you're doing, then by all means do it, but either one is fine with me. So then as far as simplifying these guys, who got a calculator yesterday? When you didn't all just like run out to buy a calculator? You did? Yeah. So if I were you, I would just use your calculator to do these calculations because then you don't have to even think about it. If you got that calculator that I talked about yesterday, that TI like 30, whatever it is, 30 TX something or other, there's a really nice button on it that looks like this. It's just like the fraction button in my math lab. So you just click that button and then you use your arrows, fill in your numerator, denominator, and it'll give you your answer as a fraction as well. So that's pretty handy. If you don't have a calculator and you want to do this in your head, when you multiply a whole number by a fraction, you divide by the denominator and you multiply by the numerator. So this is 20 divided by 5, which is 4, times a factor of 2 on top. So that gives me 8x. And then 20 times 1 is 20. And then 20 divided by 10 is 2, times 3 is 6. And then 20 divided by 4 is 5, times 1 is 5. So we get there. And now we have a pretty basic linear equation that we can solve for x. So the second step to solving equations, we don't have to do here, but we'll write it down, is to simplify each side by distributing and combining like terms. So before you solve an equation, you always want to simplify each side of the equation. So before we start moving things back and forth, doing things on both sides of the equation, you would simplify each side separately as its own expression. In this case, there isn't any simplifying to do. But if you have like 6 terms that contain x on the left and 7 terms that contain x on the right, it's much simpler to combine those into a single term on each side than to like add and subtract like 12 things on both sides. So it really just makes it a lot easier to organize and follow what's going on. So step 3 is to get all terms containing the variable on one side. And we do this using addition or subtraction only. So I really like my variables on the left side. It doesn't really matter where you get your variables. I'm just a little bit like OCD about it. So you could subtract 8x from both sides here. I'm going to subtract 6x from both sides because then my variable is going to be on the left. So 8x minus 20 minus 6x gives me 2x minus 20. And then if I subtract 6x from 6x plus 5, I'm just left with 5. Next step is to get all terms not containing the variable. On the other side. And again, we can only use addition and subtraction in this step as well. in reality, it doesn't really matter the order that you do those two in. Like if you got the terms not containing the variable on one side first, that would be okay. We've just noticed that when we encounter some of the special cases, like when there's no solution or multiple solutions, that students sometimes get to a point where it just looks weird and it's like, what the heck do I do now? If you do it the other way around. So if you do the constants first and then the variable terms, sometimes you can get to an equation that just looks really funky, and you kind of seem to lose one side. So we put it in this order just because it seems to work out a little bit nicer for those special cases. It's not wrong to do it the other way. So I'm going to add 20 to both sides. So if I add 20 to the left side, I'm left with 2x. If I add 20 to the right side, I get 25. And then the very last step is to divide both sides by the coefficient of the variable. So the coefficient is just the numerical factor in a term. So in that variable term 2x, it's got a factor of 2 and a factor of x. The numerical factor is 2, and so that's the coefficient, is 2. So it's just that number that's being multiplied by your variable. So if I multiply the left side by 2, I get x. If I multiply the right side by 2, I get 25 halves. And we're just going to leave it like that. So in general, you'll leave your answers as simplified fractions. The only exceptions to that are if there are decimals in the original problem, then it's appropriate to have a decimal answer. Or if it's an application problem, right? Like if I was like trying to find like how many feet of rope I need to buy from the hardware store, it wouldn't make sense for me to say 25 halves feet of rope because nobody talks that way. It would make more sense for me to say 12 and a half or 12.5 feet of rope. So if it's an application problem and you're writing like a sentence in English as your answer, then it makes sense to use a decimal or mixed number. But otherwise, we just leave it as a fraction. That's one of the frustrating things in my math lab. If you use the wrong form of a number, then it marks it wrong. But there's always there's like a blue line underneath, like a sentence in like blueprint underneath the answer box that always says something like enter a fraction or an integer or something like that. So you know what they're looking for. But in general, it's always going to be a fraction except for those two cases I just mentioned. So far, so good? Okay, let's do some more. So let's solve x plus 10 plus 1/3 x. I think that's not clear enough. Third x equals 1 plus 1/5 x. So I'm going to have you guys solve this one, but before you get started, I just wanted to make a quick note about that first term. So terms in general are separated by addition, subtraction, and the equals sign. So this entire thing is one term, which you'll treat just like you treat like 1/3 x, right? So like we have 1/3 times a variable, and then over here we have -2/15 times x plus 10, which is really just another variable. It just happens to be written in the form 10 more than whatever x is. So what that means is when you multiply by your LCM, we aren't going to multiply that x plus 10 by our LCM separately from the -2/15, right? We're just doing our LCM times -2/15. You'll simplify that and then distribute to your x plus 10. So you don't want to distribute first. You want to clear those fractions first and then distribute the new coefficient that you get. So go ahead and give this guy a shot, and then we'll go over it together. We want to multiply by 15, which is 15 over 1, as opposed to 15 over 15. So this is equal to 1, right? We want it to be equal to 15. So it'll be 15 over 1. Because we don't need to make the denominators the same. We just want to multiply by the number 15. Because that'll cancel off our denominators. Whereas if we multiply by this, and these 15s will cancel, but we still have that 15 down.
Yes, then what I do is I do this.
Right, and so what I'm saying is you want to start with this. Because all this is just extra work you don't have to do. So you're just going to start by multiplying by 15 over 1. Just like we did up here.
I do it differently, I think.
A good idea to write down what I write down, because then you have to see it. So start with 15 over 1. Then go from there. So I just mean what you're doing right here, you want to do from the very beginning. Like, you don't have to do any of that. You're going to multiply 15 by negative 2 over 15. So we'll do this in the next step. So we're going to multiply 15 by this term, 15 by this term, 15 by this term, and 15 by this term. So all 4 terms, you'll multiply by the number 15. So when you distribute, that's going to be, well, let's do it, and then you'll see. No, I mean, like, you can do it. What do you get when you multiply 15 by negative 2 over 15? Well, the 15's cancel, right? Isn't 15 divided by 15 1? So 15 divided by 3 is 5. So then you just get 5x. Okay, so let's have a look at it. So this process of clearing fractions is, I mean, when I first learned it, it just seemed convenient, right, to get rid of all those fractions and not have to work with messy numbers. But in addition to that, it's also helpful when we get to equations like this one where the variable is in the denominator, because in order to get the variable by itself, you got to get all your variables on the same level, right? So we have to somehow get all those variables out of the denominator, and the way that we do that is by clearing fractions. So this process is something that we'll use quite a bit throughout the semester as we get into more complex equations, which is why it's so important to start practicing with it now, even though there are other ways to solve equations that just have numbers in the denominator. So we're going to multiply by what on both sides? 15 is our LCM. So we have 15 times negative 2/15 times x plus 10. And then 15 times 1/3 x. 15 times 1. And then 15 times 1/5 x. So when I multiply 15 times negative 2/15 times x plus 10, think about multiplying three numbers, right? You multiply the first two, and then you multiply the result of that by the third one. So the three things we're multiplying here are 15, negative 2/15, and x plus 10. So 15 times negative 2/15 is just negative 2. And then we're going to multiply that by x plus 10. Because there's multiplication between the negative 2/15 and the x plus 10, we don't distribute multiplication over multiplication, right? If we were multiplying 2 times 3 times 5, we would say 2 times 3 is 6, and then multiply 6 times 5. So same idea. It doesn't look like we're just multiplying three numbers because x plus 10 looks different than just a single number. But in reality, we're multiplying 1, 2, 3 values. So we multiply the first two, and then we'll multiply that by the third. So far, so good? Okay, then the other terms are a little bit simpler. So 5x equals 15 plus 3x. Right, again, we have 15 over 1. If you think about it in terms of like taking a third of the number 15, right, that's just 5. And then we'll distribute that negative 2. And combine like terms. And then I want to get all terms containing my variable on the same side. So I have to subtract 3x from both sides. What do you get if you subtract 3x from the left side? Sorry?
You don't have an x.
Right, so you end up with what on the left side? Yeah, good. And what do you get if you subtract 3x from the right side? 15. Excellent. What can you say about that statement?
No solution.
So, right, so negative 20 equals 15 is simply not true, right? And it's never going to be true, which means there is no value of x that I can put into this equation that's ever going to make the two sides equal to one another. And that's true all the way down the line. So if your final equation is never true, your original equation is never true. And that's when we say that the equation has no solution, just like you guys said. Good. So in general, as far as your answer to these problems goes, you want to think about if somebody asked you what are the solutions to that equation. The solution to the equation isn't negative 20 equals 15. The solution is, well, there aren't any, right? So if I ask you what are the numbers that you can put in for x, you'd say there aren't any, right? None. So we need to make that conclusion that there's no solution. A similar situation, I'm just going to do a really simple one. if I want to solve this equation. So we don't have any fractions to worry about. So the first thing we're going to do is distribute. So we get 3x plus 12 minus 5 equals 3x plus 7. And combining like terms gives me 3x plus 7 equals 3x plus 7. So kind of at this point we start to see something strange going on, right? Because both sides are the same. Which really you could stop here and make your conclusion. But if we were to say, okay, I want to get all my terms containing x on one side, we'd subtract 3x from both sides again, and then we'd get 7 equals 7. What can you tell me about the statement 7 equals 7?
True.
It's true, yeah, exactly. It's always true, right? So there's no number that I could put in for x that would make 7 not equal to 7. Right? Or if you look at the step above it, there's no number that I could put in for x that would make 3x plus 7 not equal to 3x plus 7. So what numbers are solutions to this equation?
Infinite.
Yeah, there's an infinite number of values. Any number is a solution. No matter what I put in for x, both sides are going to be equal to each other. And so just like with the last example, if negative 20 is never equal to 15, then the original equation is never true. If 7 is always equal to 7, then the original equation is always true. And so we say all real numbers. Because I can choose any real number, put it in for x, and this equation will still be true. So these are kind of our special cases. They only come up if all of the variables end up subtracting or adding off, right? So we end up with a number equal to itself, which makes it always true, or a number equal to some other number, which makes it never true. If you still have an x, even if x is equal to, say, 0, that's still a solution, right? That would mean that 0 is the only number I can put in for x that would make the equation true. So only if all of your x's end up subtracting off will you be in a situation with no solution or all real numbers. Does that make sense? So those are sort of the three things you want to focus on tonight is clearing fractions, even if it's a little uncomfortable and you'd rather do it a different way. Focus on that so you can get comfortable with it before we get into even more complex equations where we have to clear fractions. And then looking out for these special cases where we have more or less solutions than we usually do. So again, tonight your homework